Hello, today we are talking about differential equations, and specifically we will be talking about differential equations whose solutions will be an exponential growth or exponential decay equation, which means we'll have an e raised to a power as our solution to the differential equation. So let's start with what we've been given, and we know the population of the little town of Scorpion Gulch is now 1,000 people. Well, that tells me something. That tells me that now, which we're going to call at time 0 years, that our population is 1,000 people. Now, that doesn't start me off on my differential equation, but that's information I will use to solve for my differential equation. It also tells me the population is presently growing. That's going to be a rate of change. So it is growing at about 5% per year, which means I'm going to increase by 5% every year. So the change in my population over time, the rate of change of my population, is going to be 5% of the population. Now, to write 5% mathematically, we would write that as 0.05, and then times the population would be times p. So here's our differential equation. What we need to do is write a differential equation that expresses the population as a function of time. Check, we have done that. Solve it to find an equation that expresses the population as a function of time. So now I need to solve this and get an equation where p equals something. So the first thing that I need to do is I need to separate the variables. I didn't spell that right, did I? Separate. I don't know which is right. I think it's separate. Separate the variables. And what that means is I'm trying to get dp with p and dt with t if there is a t. Now, to do this, we're only going to use multiplication and division. Okay, we're not going to use anything else. Multiplication and division is all we are using when we try to separate our variables. Okay, that's it. So what I'm going to do first is I'm going to multiply by dt on both sides. Basically, I'm cross multiplying, only I didn't write it as a second fraction. So I multiply by dt. And so my dt is on the right, my dp is on the left, which means my p needs to be on the left, which means I need to divide both sides by p. And when I do that, I get dp over p equals 0.05 dt. I apologize, I probably should use different variables. So this is called separating the variables. So that's what I've done so far. The next thing I want to do is rewrite this in calculus-friendly terms before I take an antiderivative. So I'm going to rewrite in calculus-friendly terms. And when I do that, I'm going to write it as 1 over p dp equals 0.05 times dt. So this is my calculus-friendly terms, and then what I really want to do is find the antiderivative so that I can solve for p. So step 3 is to take the antiderivative of both sides of the equation. So we are simply going to take the antiderivative of both sides of the equation. And when I do that, I need to recognize my antiderivative, and the antiderivative of 1 over p is a natural log, but more specifically, it's the natural log of the absolute value of p. As we discussed in the last lesson, I should really have a plus c on this side, but what I'm going to do is I'm just going to write 1 plus c on the other side where the t is. So I'm going to end up, when I take the antiderivative of 0.5 dt, is 0.05 t plus some constant. So again, in step 4, we're going to add the plus c to one side. Okay, to the side with the t. We're going to add our constant. And again, it's just because I could subtract both sides by the constant on the left, which is going to put all the constants on the right as one constant. And I don't need to know the left and right constants. I just need to know one of the constants. So I've done this. This is great. So what I need to do at this point is I need to solve for p, but I also have to deal with this absolute value. So I'm going to go ahead and deal with the absolute value right now. So to deal with the absolute value, I need to look at this situation because I can't take the natural log of a negative number. But what am I talking about? I'm talking about the absolute value of p, and p represents a population, which means, can a population be negative? So, no, I can't have a negative population. So my population is always positive, which means I don't actually need my absolute values anymore because I know that p will always be positive. So I can just rewrite it like this at this point. So to get p out, that's what I need to do. I need to get the variable now out of the natural log. So to do that, I'm going to take e raised to the of both sides of the equation. I'm not sure the technical term for that, but we're just going to call it take e to the of both sides. So I'm going to do e raised to the and e raised to the. So e raised to the natural log of p will be equal to e raised to 0.05 t plus c1. And we talked about this last lesson. E to the natural log of p is just p. And e to the 0.05 t plus c1 is the same as some constant times e to the 0.05 t, because e raised to the c1 is still a constant. Again, I don't care what each individual constant is. I actually only care what this one is. So I now have an equation for p. So I need to find c. So that's really my second to last step. I need to find my constant, and I'm going to do that by using the initial condition. Now we wrote that at the very beginning. We talked about the population of Scorpion Gulch is now 1,000 people. So for us, when t was 0, the population was 1,000. So I'm going to plug those values in. 1,000 goes in for p, and then I'm going to plug in 0 for t. And this is c e raised to the 0. And anything raised to the 0 power is just 1. So when I evaluate this, I get 1,000 is equal to c times 1, or c equals 1,000. Now I should be able to write my differential equation is 1,000 e to the 0.05 t. There is the solution to the differential equation in the problem in example 1. Again, if you have any questions, go ahead and write those down so you can bring them to class next time. Now we're going to move on to example 2. So you got a couple of options. Either you write really small or you get another piece of paper. So whichever you want is fine. But there's a lot of things we're going to be doing on this paper. So if you write big, then you need to get another piece of paper. If not, you'll be able to squeeze this on and I'll help you through that. So for our punctured tire problem, example 2. We run over a nail in the car. As the air leaks out of your tire, the rate of change of air pressure, hold on, that's a differential equation. The rate of change of air pressure, I'm going to call that dp dt. I don't know why I keep using p and t. inside the tire is directly proportional to that pressure. So directly proportional is K times the pressure. So dP dt is going to equal K times P. Now we're starting with the A, B, C, D, E. Starting with A. Write a differential equation that states this fact. Okay, great. We've got part A. Part A. Okay, dP dt equals K times P. There you go. And then it says evaluate the proportionality constant, that's otherwise known as K, if the pressure was 35 psi and decreasing at 0.28 psi per minute at time 0. So I'm going to use that information to find out what K is. The rate of change was negative 0.28 at the time that the pressure was 35 psi. So I just plug those two things in. And again, the 0.28 was a rate of change. And to find K, I would simply divide. And if I solve that, K ends up being negative 0.008, I think. And as you know, you need to actually solve that and make sure that's right. Use the right number if my number is wrong. We can just call it K for right now. So I'm going to say every time I see a K, that's actually the value. So I could rewrite this if I wanted to as dP dt is equal to negative 0.008 times the population. Or once you have established what K is, you can still use the letter K in there if it makes it easier. Now, I would go ahead and use the K. But what I would like for you to do right now, I want you to solve this differential equation. They also gave us an initial condition. So we'll use that in part B. They said at time 0, the pressure was 35. I'm going to scroll up for a second. And they told us that at time 0, the P was 35. So they gave us that when they gave us the rate of change. So we're going to use that to find C. But I really would like you to try to evaluate your differential equation, solve this differential equation for P, and then I want you to use part B is to find that constant. Now, if you see a pattern and you can jump immediately to a solution for P involving a constant, C, you're welcome to do that. Otherwise, go ahead, separate the variables, and solve for P. But I would like you to do that right now, so go ahead and pause the video now, please. So here's my solution. In blue at the top of the screen is my final answer for P, which is 35e raised to negative 0.008 t. On the left side of your screen is my solution in getting there. So again, pause the video if you did not get this correct so that you can figure out where you went wrong. Now in part C, we are asked to give a sketch of this graph, and this we should be able to sketch. Let's start with what e to the x looks like. And a sketch of e to the x looks like this. And right here is where it's e raised to the 0, which is at 1. Now, if I have a negative x, because when I look at my differential equation, I have a negative 0.008 t. So what that means is if I have y equals e to the negative x, I've reversed my x's. I'm going to reflect that over the y-axis. So it's going to look like this, and again, that is at 1. For my particular graph, I'm going to graph P. We have when t is 0, we know that we are at 35. So a sketch of the graph is going to look like this, and the value where it crosses the y-axis is at 35. So there is my sketch for part C. Part D says, what will the pressure be at 10 minutes after the tire was punctured? So all that is a substitution. For part D, I have the population is 35. e raised to the negative 0.008t. And the question is, the population is what when the time has been 10 minutes? Sorry, the tire pressure, not the population. So I'm just going to insert a 10, and I'm going to pick up my calculator, and I'm going to figure out what that is. I think. Yes. So at this point, you should be able to pick up your calculator and evaluate that. And I believe if you do this, you get 32.3090 psi. So again, go ahead and make sure that you get that when you plug that into your calculator. Moving on to part E, I'm going to go back up a little bit. For part E, it says the car is safe to drive as long as the tire pressure is 12 psi or greater. So that's where P is equal to 12 or bigger. So for how long after the puncture will the car be safe to drive? So I really want to know, well, at what point does the tire pressure get down to 12? So the equation that I'm solving now is 12 is equal to 35 e to the negative 0.008 t. So to do this, I'm going to use logarithms. I'm going to go ahead and work this down by hand as much as possible before I pick up my calculator. So the first thing I'm going to do is divide both sides by 35. And when I do that, on the left side, I get 12 divided by 35. And now I have e raised to an exponent, and the exponent is my variable. And so I need to take the natural log of both sides. So I have the natural log of 12 over 35, and 12 divided by 35 is positive, so I don't need to worry about that. And then I have the natural log of e to the negative 0.008t. Now, the natural log of e raised to something is just that exponent. So I have this. To get t by itself, I need to divide by that decimal. So in my calculator, I'm first going to evaluate the natural log of 12 divided by 35. Then I'm going to divide by negative 0.008. So go ahead and pick up your calculator and evaluate that. And what I got was 133.8051 minutes. And again, the question started out as a word problem. We need to answer it in words. So to answer the question, the car will be safe to drive for 133.8051. Wish I could write. 133.8051 minutes. So again, be sure to come to class with any questions that you have, and I hope you have a wonderful evening.